Hello, my name is Noah Bewley. This is my video for Physics Lab 4 for 2212. Fundamental ideas for this lab, which dealt with RC circuits and simple circuits, include the loop rule, the node rule, the additivity of resistance and capacitance based on if they're in series um, or in parallel, and Ohm's law, V equals IR. Loop rule referring to the idea that um, if you make it all the way around a circuit once to the exact same point, the values of IV and R at that point are going to be the same, um, regardless of the path you take, because you're at the same place in space. The node rule being the idea that once you hit a node, the current you have going into the node is going to equal the net current you have coming out of the node. Additivity of resistance and capacitance varies if you're talking about capacitors resistance. Resistors are more effective in series, capacitors are more effective in parallel. Model descriptors, I use the online model. It's an online idealized model. Um, and you had a few assumptions that were pretty vital to it functioning. Zero resistance through ammeters and wires, and infinite resistance through a voltameter. So the voltameter allowed negligible amounts of current to flow through it, and that'll be relevant. For part one, this is just a simple circuit. The predictions I made before running this simulation were due to the node rule. A1 is going to be equal to A2. And what I mean by that is there are no nodes between each ammeter, so the current through each ammeter should be identical because every bit of current flowing through the first has to come out the second to actually complete the loop of the circuit. And using resistance additivity, so because they're in series, you just add these as you normally would. So you have a additive resistance of 147 ohms between those two resistors. And using V equals IR, you can come up with 0.02 amps. Those predictions were entirely correct, partially because it's an idealized model, so it followed these rules very well. And when the ammeter was replaced completely by a voltameter, the current dropped to zero. That's because what I was just talking about, the voltameters in the simulation have infinite resistance. They allow no current to flow. So basically, it was just measuring the potential difference on either side of the two batteries in series, which was 3 volts. That's why it read 3 volts. Continued. This graphic is a little bit skewed. I can't really fix it whenever I'm doing these recordings. I don't know why. But the readings of delta V from circuit segments. This is just me completing the graph they were giving you. You see that at each of the batteries, the voltage jumps up 1.5 for each battery, and then at each resistor, you see it decrease across the resistor back to zero. And you can see that this graphic also follows the loop rule because beyond point H, you hit point A again. So you can see that at that singular point coming from either direction, the voltage at that point would be the same. So it follows the loop rule. When the ammeter was moved to be in parallel with the resistor, the observed resistance dropped and overall current increased. The reason for this is because the ammeter in the simulation has effectively no resistance. So once you hit that node where you have the ammeter and the resistor in parallel, a lot more current is going to flow as a net over that because the ammeter has no resistance and it allows more current to flow um, through that segment of the circuit. So that's why there was a net current increase and the net resistance of the entire circuit decreased when we added that ammeter in parallel to the resistor. Part two, this used 20, 10, 20, and 30 ohm light bulbs and a capacitor at 200 millifarads and a 9-volt battery. Because there was a capacitor, you saw a charging of the capacitor and a discharging the capacitor. As the capacitor charged, overall current decreased as those charges built up on the plates. When you disconnected the battery, it allowed that electromotive force from the capacitor to discharge and fuel the light bulb. We saw a greater charging time and discharge time with the 20 ohm light bulb because it allows less current to flow and extends the period of the discharge of that capacitor. RC discharge profile. This plot in Excel was made from experimentally sampling values of delta V over time. This is a linearized form of an RC equation, and experimentally from the slope of that, the line of best fit from that, what we plotted in Excel, the experimental RC was seen to be 6 seconds, and the theoretical RC, literally resistance 30 ohms for the light bulb in this case, times capacitance 200 millifarads or 0.2 farads, was equal to 6 seconds. The reason that lined up, there was very little error in this entire lab, is simply due to the fact that it's a simulation that's built on these idealized laws. So what if you were doing this lab in real life and use an actual ammeter? The actual ammeter in real life has a certain resistance, so it would sample lower rates of current as compared to the virtual ammeter, which had zero resistance. It literally was just telling you exactly how much current would be going through. Same thing with the wires. Real wires have resistance, and these theoretical wires did not have any sort of resistance. What if you're doing this lab in real life and used a real battery to charge a capacitor? Because real wires have resistance, you'd see a capacitor charge over time. It would charge in relation to the amount of resistance of the wires. If wires really had no resistance, it would charge immediately as the second electromotive force could kick in. Um, that. Overall conclusions, when using idealized relations, it's important to assess the similarity of the real materials you're using to the ideal ones. Real wires don't have no resistance. The node and loop rule are valuable tools to understand circuit behavior, however simple they may be. They're very vital. And in an RC circuit, current varies consistently with time based on that RC constant, whatever circuit you're talking about. All right, thank you.